Algorithms. What are algorithms? Why is the study of algorithms worthwhile? What is the role of algorithms relative to other technologies used in computers? In this presentation, I will be going through these questions. Let's start with a definition. What is an algorithm? Informally, an algorithm is a well-defined computational procedure that takes some value or set of values as input and produces some value or set of values as output. An algorithm is thus a sequence of computational steps that transform input into output. We can also define an algorithm as a tool for solving a well-specified computational problem. A problem specifies in general terms the desired input-output relationship. The algorithm describes a specific computational procedure for achieving that input-output relationship. For example, one might need to sort a sequence of numbers into non-decreasing order. This problem arises frequently in practice and provides fertile ground for introducing many standard design techniques and analysis tools. Here is how we formally define the sorting problem. Input: a sequence of n numbers, a1, a2 up to an. Output: a permutation of the input sequence a1, a2 up to an such that a1 is less than or equal to a2 is less than or equal to up to is less than or equal to an. Another example, given the input sequence 31, 41, 59, 26, 41, 58, a sorting algorithm returns as output the sequence 26, 31, 41, 41, 58, 59. Such an input sequence is called an instance of the sorting problem. In general, an instance of a problem consists of input needed to compute a solution to the problem. An algorithm is said to be correct if, for every input instance, it holds with a correct output. We say that a correct algorithm solves the given computational problem. An incorrect algorithm might not hold at all on some input cases, or it might hold with an answer other than the desired one. Contrary to what one might expect, incorrect algorithms can sometimes be useful if their error rate can be controlled. What kinds of problems are solved by algorithms? Sorting is by no means the only computational problem for which algorithms have been developed. Practical applications of algorithms are ubiquitous and include the following examples. 1. The Human Genome Project. It has the goals of identifying all the 100,000 genes in the human DNA, determining the sequences of the 3 billion chemical base pairs that make up the human DNA, storing this information in databases, and developing tools for data analysis. Each of these steps requires sophisticated algorithms. 2. E-commerce. It enables goods and services to be negotiated and exchanged electronically. The ability to keep information such as credit card numbers, passwords, and bank statements private is essential. Public key cryptography and digital signatures are among the core technologies used and are based on numerical algorithms and number theory. 3. The Internet. It enables people all around the world to quickly access and retrieve large amounts of information. In order to do so, clever algorithms are employed to manage and manipulate this large volume of data. Suppose computers were infinitely fast and computer memory was free. Would you have any reason to study algorithms? The answer is yes. If for no other reason than that you would still like to demonstrate that your solution method terminates and does so with the correct answer. If computers were infinitely fast, any correct method for solving a problem would do. You would probably want your implementation to be within the bounds of good software engineering practice, i.e., well designed and documented. but you would most often use whichever method was the easiest to implement. Of course, computers may be fast, but they are not infinitely fast. And memory may be cheap, but it is not free. Computing time is therefore a bounded resource, and so is space in memory. These resources should be used wisely, and algorithms that are efficient in terms of time or space will help you do so, no matter whichever method was the easiest to implement. Efficiency. Algorithms devised to solve the same problem often differ dramatically in their efficiency. These differences can be much more significant than differences due to hardware and software. As an example, in upcoming presentations, we will see two algorithms for sorting. The first, known as insertion sort, takes time roughly equal to C times n squared to sort n items, where C1 is a constant that does not depend on n. That is, it takes time roughly proportional to n squared. The second, merge sort, takes time roughly equal to C2n log n, where log n stands for log base 2n, and C2 is another constant that also does not depend on n. Insertion sort usually has a smaller constant factor than merge sort, so that C1 is less than C2. We shall see that the constant factors can be far less significant in the running time than the dependence on the input size n. Where merge sort has a factor of log n in its running time, insertion sort has a factor of n which is much larger. Although insertion sort is usually faster than merge sort for small input sizes, once the input size n becomes large enough, merge sort's advantage of log n versus n will more than compensate for the difference in constant factors. No matter how much smaller C1 is than C2, there will always be a crossover point beyond which merge sort is faster. For a concrete example, let us pit a faster computer, computer A, running insertion sort against a slower computer, computer B, running merge sort. They each must sort an array of 1 million numbers. Suppose that computer A executes 1 billion instructions per second, and computer B executes only 10 million instructions per second, so that computer A is 100 times faster than computer B in raw computing power. To make the difference even more dramatic, suppose that the world's craftiest programmer codes insertion sort in machine language for computer A, and the resulting code requires 2n squared instructions to sort n numbers. Here, C1 equals 2. Merge sort, on the other hand, is programmed for computer B by an average programmer using a high-level language with an inefficient compiler, with the resulting code taking 50n log n instructions, so that C2 is equal to 50. To sort 1 million numbers, computer A takes 2000 seconds, while computer B takes 1000 seconds. By using an algorithm whose running time grows more slowly even with a poor compiler, computer B runs 20 times faster than computer A. The advantage of merge sort is even more pronounced when we sort 10 million numbers, where insertion sort takes approximately 2.3 days. Merge sort takes under 20 minutes. In general, as the problem size increases, so does the relative advantage of merge sort. By using an algorithm whose running time grows more slowly, even with a poor compiler, computer B runs 20 times faster than computer A. The advantage of merge sort is even more pronounced when we sort 10 million numbers, where insertion sort takes approximately 2.3 days. Merge sort takes under 20 minutes. In general, as the problem size increases, So does the relative advantage of merge sort. Algorithms and other technologies. The example which we just went through shows that algorithms, like computer hardware, are a technology. Total system performance depends on choosing efficient algorithms as much as choosing fast hardware. Just as rapid advances are being made in other computer technologies, they are being made in algorithms as well. You might wonder whether algorithms are truly that important on contemporary computers in light of other advanced technologies, such as hardware with high clock rates, pipelining, and superscalar architectures, easy to use, intuitive graphical user interfaces, object-oriented systems, and local area and wide area networking. The answer is yes. Although there are some applications that do not explicitly require algorithmic content at the application level, e.g., some simple web-based applications, most also require a degree of algorithmic content on their own. For example, consider a web-based service that determines how to travel from one location to another. Its implementation would rely on fast hardware, a graphical user interface, wide area networking, and also possibly on object orientation. However, it would also require algorithms for certain operations, such as finding routes, probably using a shortest path algorithm, rendering maps, and interpolating addresses. Moreover, even an application that does not require algorithmic content at the application level relies heavily upon algorithms. Does the application rely on fast hardware? The hardware design used algorithms. Does the application rely on graphical user interfaces? The design of any GUI relies on algorithms. Does the application rely on networking? Routing in networking relies heavily on algorithms. Was the application written in a language other than machine code? Then it was processed by a compiler, interpreter, or assembler, all of which make extensive use of algorithms. Algorithms are at the core of most technologies used in contemporary computers. Furthermore, with the ever-increasing capacities of computers, we use them to solve larger problems than ever before. As we saw in the above comparison between insertion sort and merge sort, it is at larger problem sizes that the differences in efficiencies between algorithms become particularly prominent. Having a solid base of algorithmic knowledge and technique is one characteristic that separates the truly skilled programmers from the novices. With the modern computing technology, you can accomplish some tasks without knowing much about algorithms, but with a good background in algorithms, you can do much, much more. Spiders.co is the name of this channel. Our Instagram handle is at _spiders.co_. Please like and subscribe, and also follow us on our Instagram. Thank you for watching. This has been wonderful.